We are all aware of the fact that motion since 1905 is relative and depends upon observers and how they interact with their environment. This gives rise to new insight on the nature of space and time. To define these concepts more rigorously, one needs to introduce the notion of reference frames, observers, and measurements. So let us start by defining these concepts and build upon it the marvelous theory of special relativity. Reference frames. In order to define a reference frame, one requires three ingredients: a coordinate system, an environment, and an observer sitting in this coordinate chart. The environment is basically the physical system that we are dealing with. An observer is an experimental apparatus equipped with measuring devices, such as rods and clocks, and performing multiple measurements on such a physical system. A coordinate chart is used to represent mathematically a given physical system. Each chart is associated to an observer, and each observer is put in a physical environment. We examine different physical systems. There are many, but two main physical systems are inertial and accelerated systems. Inertial systems are physical systems that are stationary, that is not moving with respect to another physical system. So, if one associates an observer that's not moving in such a physical system with its chart, then one would have defined an inertial frame of reference. The observer then can perform numerous measurements and observations. These special frames might also be moving with constant velocity without any acceleration. This brings the discussion to another class of reference frames, which are non-inertial frames. By taking an inertial frame and relaxing the stationary assumption of the observer, we let the observer be accelerated with its chart. Such reference frames are called non-inertial or accelerated frames, and they are used in many physical problems such as rotating bodies, planetary motion, or even in gravitational theories such as general relativity, which is beyond the scope of this video. The collection of those reference frames defines the family of observational frames. Cartesian frames and Galilean invariants. Cartesian frames are charts equipped with coordinate axes, all starting from a fixed origin, that helps one to locate a particle in terms of the coordinate axes. The axes are perpendicular and the unit vectors are orthonormal. One can then equip observers with rods and clocks. Imagine two such Cartesian frames, but with one stationary denoted as r, and one moving with respect to the other with a constant velocity v, denoted as r prime. The question is, how can we relate one to the other by means of observers? We start with the principle in physics, which is that all laws of physics are equivalent in all inertial frames. This suggests that an observer's measurement outcomes in r would give the same outcomes in another inertial frame. What about r prime? Let us start introducing Galilean invariance, which states that time is absolute. A physical event r will have positional coordinates r equals x, y, z and a time of t, whereas r prime will have coordinates r prime is equal to x prime, y prime, z prime, and a time t prime. By the absoluteness of time, one can synchronize both clocks and assume t is equal to t prime. Because r prime is in relative motion to r, consider a point object whose position is given by the functions r prime of t in r prime and r of t in r. Then we would have that r prime of t is equal to r of t minus vt. Then, by differentiation, one gets that a prime of t is equal to a of t. The above equation shows Newton's laws of mechanics, if valid in one inertial frame, must hold for all inertial frames. But it is assumed to hold in absolute space and with absolute time. Therefore, Galilean relativity holds. Maxwell theory and Galilean invariance. The absoluteness of time and space is what makes relativity Galilean. However, according to Maxwell's theory, the speed of propagation of electromagnetic waves in a vacuum is a constant c. This creates an important problem, that is, Maxwell's electromagnetism is not invariant under Galilean transformations. Therefore, one needs to either modify electromagnetism to be Galilean invariant, or modify Galilean transformations by taking into account the constancy of the speed of light. History and nature has chosen to modify Galilean invariance into the so-called Lorentz invariance, which takes into account the speed of light. Einstein's postulates and Lorentz transformations. Einstein postulated that we keep Galilean relativity as it is, but relax the absoluteness of time postulate. That is, the laws of physics are invariant in all inertial frames, and the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or observer. These two postulates imply new sets of transformation rules between inertial frames called Lorentz transformations. What we notice is that t prime does not equal t, which means that the absoluteness of time is broken and replaced by relative time. Each observer has its own synchronized clocks before motion. After motion, their clocks will give different results. Such inertial frames are called Lorentz frames, hence we have a very interesting phenomenon occurring in real life. Rods and clocks in special relativity. We encounter many possible real-life examples of the effects of special relativity, that is time dilation and length contraction. Consider two observers, one sitting on the ground on Earth and another one in a spaceship moving at the speed of light. Before the launch, both observers synchronize their clocks and rods. After the launch, one would see that because of Lorentz invariance, the observer sitting on Earth will observe a shortening of the length of the spaceship and will predict the time of the observer inside the spaceship is running much slower. However, the observer inside the spaceship does not measure any changes to his own clocks and rods. We can even extend this situation, where the spaceship flies at the speed of light for about a year, and on the comeback, the observer would have aged by a single year, but the one on the ground would have aged by several years. In turn, the Lorentz invariance has suggested Einstein and Minkowski to combine space and time into a single structure called spacetime, where time and space are on equal footing. This is the essence of special relativity.